All right. Two language model, the sensory grounding for meaning and understanding. The answer is yes.
Oh, we can't hear you, right?
You can hear me. Now you can hear me. Hopefully. So the answer is yes, hopefully. I mean, certainly. So first, current AI systems or machine learning-based AI systems really suck compared to human and animals in terms of their ability to learn. So we all know the limitations of supervised learning. It requires many labeled samples. Reinforcement learning requires insane amounts of trials. And obviously we're missing something big because we still don't have domestic robots and self-driving cars. And so how is it that animals and humans can learn so fast? So in recent years, self-supervised learning has been sort of taken over the world. And they do require a large number of unlabeled samples, but unlabeled samples are cheap, so that's a big advantage. But the problem is the current systems really make really stupid mistakes, and they can't reason, they can't plan, and they don't really have kind of an understanding of the world, and that includes large language models. I'll come to this in a minute. In comparison, animals and humans can learn new tasks extremely quickly, relying on their background knowledge about how the world works. They do understand how the world works. They have pretty sophisticated world models. They can reason, they can plan, and they have common sense. That's perhaps the accumulation of knowledge that allows them to have common sense. So current machines, not so much, or a little bit, but it's very superficial, and we need to make them non-superficial. So self-supervised learning, SSL, has really taken over the world. And it's the idea that you train a system to predict missing information, temporarily missing information. So you show a piece of a video clip, and you ask the system to predict what's going to happen next in the video clip or some other parts of the video clip, and then you reveal what happens, and you expect the system to be able to, by training itself to predict, to have some understanding of the underlying reality. And this doesn't work. Like, we don't know how to do this today, or not very well, at least. We can do it with text. It works really, really, really well with text, but not yet with video or any kind of other sensory information. So if the answer to the question of the debate is yes, but not yet, we don't know how to do it yet with AI systems. So SSL has been extremely successful over the last 7 or 8 years or so, where the idea of filling in the blanks is you take a piece of text, you corrupt it in some way by removing words or substituting them, and then you train some giant neural net to predict the words that are missing. And in the process of doing so, the system learns appropriate representations of language that incorporate semantics and grammars and syntax and all kinds of stuff. And it's multilingual, and it works wonderfully, and it's used absolutely everywhere. It's deployed commercially. You may not see it, but it's what does content moderation on all social networks today, and translation as well. Now, within this, there's a special case of this where what you ask the system to predict is not random words in the text, but just the last word. So you have a gigantic neural net with tens of millions, hundreds of millions of parameters, and you strictly train it to predict the last word in a window of text that typically has a few thousand words, something like 2,000 words. And when you have trained the system, you have it generate one word or a token, which may be a subword, and then inject that subword into its viewing window, and then generate the next word, and then inject that into the viewing window, generate the next word. This is called autoregressive generative models, and in the case of text, it's autoregressive large language models, if they're large. So I'm going to argue for the fact that those things also suck. They're amazing in many ways, okay? But they're nowhere near what's required for human-level intelligence. So those systems output one token after another. The encoders and predictors are transformer architectures, which I'm not going to go into the details of. They typically have billions to hundreds of billions of parameters, going towards trillions. They're trained typically on hundreds of billions or trillions of tokens gathered from all the text ever written by anyone. They're available online. And that creates a problem because we don't know what the training set is. We don't have a test set because those things have been trained on the entire text of the world. So if you ask them a question, you don't know if it's seen it or not, because if it's ever been specified, the system has been trained on it. And the modern systems, as soon as you ask them a question, they get fine-tuned with the answer, so you can't ask the same question twice, or you won't get the same result. So there's been a bunch of those models over the years, and an interesting phenomenon appears, which is that as you make them bigger and you train them on more data, there is sort of emergent properties. They seem to be kind of understanding more and more about the world when you make them bigger and train them on more data. The latest one being GPT-4, which nobody knows how it's built, but ChatGPT is an autoregressive LLM. And then Llama from FAIR, that was essentially open source recently, is that. Alpaca is kind of an improvement on Llama by Stanford University. So they're kind of amazing, but they make really, really stupid mistakes sometimes. Completely non-factual statements, inconsistent answers, particularly if the answer is long. Logical errors. They have very limited reasoning abilities. There is no way to control them for things like toxicity or things like that. It's very, very difficult. And it's because they don't have any knowledge of the underlying reality. So they're trained purely from text, and they really don't have any knowledge of the underlying reality that all of us share and assume is part of intelligence. Those things don't have it. So you ask them questions that can only be answered by some sort of physical understanding of reality, and they can't answer it unless a very similar situation has been specified in their training set, and they remember it. And they have like a major flaw, which is that because they're autoregressive, they produce one token after another. Let's imagine we have the set of all possible sequences of tokens, and within this set there is a small set, which is the set of correct answers, if you want. And imagine there is a certain probability E for the system to make a mistake, produce a token that takes you outside the set of correct answers. And that's the average probability for making an error. So the probability that the system will produce an answer of size n that is correct is 1 minus E to the power n. And that's an exponentially divergent process. So those systems, as soon as they start producing too many tokens, will start spewing nonsense because they are autoregressive. They don't reason, right? They don't plan their answer. They just produce one token after another reactively. And it's not fixable, in my opinion. It's not a popular opinion among my colleagues, but I don't think it's fixable. So I have a prediction, which is 5 years from now, nobody in their right mind would be using any autoregressive LLM. Okay. It's a temporary thing that we have to deal with, but they'll disappear. So they really suck. I mean, they're wonderful, they are helpful, they help us, start writing text and everything, but they're nowhere near human intelligence, and they are not a good path towards that, although they have some of the characteristics. They are an off-ramp on the highway towards human-level AI. So we need systems that can understand how the world works, and that's where grounding comes in. Babies learn how the world works. There is no language involved in the first few months of life, and they learn incredibly complicated concepts about the nature of the world, things like intuitive physics and gravity and stability and the difference between animate and inanimate objects. This is a chart I stole from Emmanuel Dupuy, who is a cognitive psychologist in Paris. And this is the accumulation of knowledge that we acquire in the first few months of life that allows us, by the time we are teenagers, to learn to drive a car in 20 hours of training. And obviously, AI systems don't do this today. We still don't have self-driving cars, so we're missing something big. So I think that sort of gives us the challenges for AI and machine learning for the next few years. Learning representations and predictive models of the world, I'll come back to that concept, using self-supervised learning mostly. Having machines that can learn to reason. So basically, autoregressive LLM and most machine learning systems today are like Kahneman's System 1. They're reactive. We need AI systems that can do System 2. Basically, they can plan their answer and kind of reason before producing an answer. And systems that can learn to plan complex actions. Okay, so to approach that problem, I've written a position paper, fairly long but fairly readable, hopefully. And it's on open review, so you can comment on it. That's the URL. It's been around for several months now, since June last year. And it's based on a cognitive architecture that's built around this idea of world models. So the system has a world model, or would have, that predicts what's going to happen in the world as a consequence of its actions, and basically has a reasoning mode where it imagines a sequence of states that the world may go through as a consequence of a sequence of actions that is imagined, and then you optimize the sequence of actions so as to minimize a particular objective, a cost function of some kind, right? So the general model for this is very old. It's called model predictive control in optimal control. But we'd like to do this with complex models of the world that are learned, and then perhaps complex inference procedure that figure out sequences of actions. And we also would want to do this in ways that are hierarchical. I want to skip to that here. Okay, so that so things like this where we don't make predictions at one level of abstraction, but we make predictions at multiple levels of abstractions, which allows us to do long-term planning in sort of abstract representations of the state of the world. That's kind of a general plan. Nobody has really built this. Nobody knows how to make this work yet. But this is basically where I think AI research is going for the next decade or so. I'm advocating also for an architecture. So there's one slide I want to show that I skipped. This one. It's a bunch of recommendations that are very unpopular in the machine learning and AI community, which is that to handle the uncertainty in the prediction, we have to abandon the idea of generative models. So all the stuff that people are excited about today, they work for text, they don't work for video. And if we want to have world models that work for video, we have to abandon the idea that we're going to predict every detail in the video. So we have to use architectures that are called JEPA, Joint Embedding Predictive Architecture, which is drawn on the right here. So no generative model, no probabilistic modeling, for reasons I'm not going to explain, and no reinforcement learning, or at least minimize it. So that's it. Let me just show one set of position and conjectures. Prediction is the essence of intelligence. We've known this for a long time. Almost everything is learned through self-supervised learning, and almost nothing learned through reinforcement or supervision or imitation or anything like that. Reasoning amounts to optimization with respect to a sequence of action, optimizing an objective. I'm recommending this hierarchical JEPA architecture, but that's a technical detail. Those systems will need to have intrinsic costs and costs and objectives that determine the function they're supposed to fulfill, and that will make those systems controllable, which is not the case for current large language models that are not controllable. Those cost functions will sort of provide the equivalent of emotions, if you want, for AI systems, because they're basically anticipation of outcomes. Thank you very much.